If you listen closely, there is a moment in the universe where a sound should exist but doesn't. A burst of high-energy light flashes into the void like the opening note of a cosmic symphony, only to fall suddenly silent, as if something has swallowed the rest of the song. Recently, scientists detected a faint echo coming from a black hole. Not a real sound, but a delayed shimmer of X-ray light bending around the edge of space-time itself. But here's the strange part. The discovery made headlines for a moment, and then everything went quiet. No deeper analysis. No follow-up. As if someone pressed mute on one of the most important cosmic clues of our era. So the real question isn't what a black hole echo is, but why the silence surrounding it is so loud. And what you're about to hear next is not what the news told you. Get ready for section 2. A black hole is a place in space where gravity becomes so intense that nothing can escape. Not even light. Exactly as Albert Einstein's theory of general relativity predicted. To understand what an echo means in this context, imagine not a sound bouncing off a wall, but light itself taking a detour around the edge of a black hole. Scientists recently detected delayed flashes of X-rays coming from behind one. Proof that extreme gravity can bend and redirect light in ways that seem almost impossible. These echoes can also appear in gravitational waves, tiny ripples in space-time that carry information from regions we can never directly see. Together they form a kind of map of the invisible, a pattern revealing how matter behaves right at the edge of the event horizon. And if you think this is simply about light being bent by gravity, wait. Because there is another hidden layer that almost no one talks about. In the past few years, headlines have celebrated the discovery of black hole echoes, especially after a team at MIT revealed 8 systems in our own Milky Way where delayed X-ray flashes were detected. Other news outlets picked up studies from the Institute for Advanced Study describing new methods to catch these light echoes. Techniques that allow scientists to separate the direct emission from the delayed reflections shaped by extreme gravity. But after the initial excitement, most reports stopped at the surface. They told the public that echoes exist, yet avoided the deeper questions about their origin, their meaning, and the uncertainties that still haunt the data. They rarely mention how faint the signals are, how difficult they are to confirm, or how much disagreement still exists among researchers. And most viewers never realize that behind the apparent breakthrough lies an unsettling truth. There are echoes in the data. Yes. But there is also a silence that nobody seems eager to explain. The deeper you look into the data, the more you realize why these echoes rarely make it into the mainstream conversation. The signals are incredibly faint, often buried under layers of noise from the surrounding cosmic environment. And researchers need specialized tools like the so-called reverberation machine to even notice them. Newer techniques allow scientists to separate the direct light from the delayed reflections by taking advantage of gravitational lensing, a natural magnifying effect created when extreme gravity bends the path of light. But even with these breakthroughs, there are still walls we cannot break through. Some of the supposed echoes in gravitational wave detections are debated, with several studies suggesting they may be artifacts, s'appelle distorsion, or statistical coincidences rather than true physical events. Others propose that if these echoes are real, they might hint at structures near the event horizon that current physics cannot fully describe, something as small as the Planck scale itself. And once you realize how much of the data has been filtered, processed, and softened into silence, you begin to understand why the real story is only just beginning. Echoes matter because they allow us to measure things that were once nearly impossible to quantify. By studying the delayed flashes of light around a black hole, scientists can estimate its mass and its spin, two properties that shape how violently it twists the fabric of space-time. These echoes also give us a rare glimpse into the region right next to the event horizon, the boundary where Einstein's general relativity begins to clash with the rules of quantum physics. It is a place we can never visit and never see directly, yet through these faint reflections we can trace the behavior of matter as it falls toward the point of no return. From small stellar black holes scattered across the Milky Way to the supermassive giants at the centers of distant galaxies, every echo becomes a clue, a doorway into a branch of physics that has not yet been written. And if these echoes are truly whispers from the edge of the abyss, then perhaps the real tragedy is that we may be hearing only a fragment of a much larger cosmic symphony. One of the most intriguing discoveries came from a Stanford research team who detected X-ray flashes emerging from behind a black hole, a moment that stunned the scientific world because it provided the first direct visual evidence of light being bent so sharply that it resurfaced on the far side. Soon after, researchers at MIT identified echoes in 8 separate black hole binary systems, suggesting that these delayed signals are not rare anomalies, but may be a common feature of how black holes interact with their surroundings. And hidden inside these observations is a layer of information we barely understand: that corona, a chaotic cloud of superheated plasma around the black hole, seems to change state in ways we cannot yet predict, flickering between bright and dim, as if responding to some unseen engine. The accretion disk, a swirling river of matter spiraling inward, brightens and fades in pulses that may correspond to the black hole's feeding cycles. The data is speaking, offering hints about processes we have never fully mapped, yet not everyone is listening closely enough to hear what it is trying to say. Some researchers have argued that after 2 black holes merge, the resulting gravitational wave should not fade smoothly, but instead produce faint echoes, tiny ripples that might hint at exotic structures near the event horizon. These ideas touch on concepts like Planck scale surfaces, firewalls, or even fuzzballs, all suggesting that a black hole may not be the smooth, featureless object Einstein once described. But other experts urge caution, saying the evidence is far too weak to support such bold claims. The signals are so faint they hover at the edge of detectability, and the templates used to search for them can be ambiguous, making it difficult to know whether we are seeing a real physical phenomenon or simply the noise of the universe masquerading as something profound. This leaves us suspended between 2 possibilities. Echoes could be the first warning sign of a new era of physics, or they could be illusions formed by the limitations of our instruments. And perhaps the reason the media remains quiet is not conspiracy, but uncertainty. Because if you think we already have the answer, wait until you hear what comes next. The future of black hole research is being shaped not just by telescopes, but by algorithms, tools like the reverberation machine, an AI system designed to sift through mountains of X-ray observations, are already uncovering echoes that human analysts would have missed entirely. As new observatories come online, from next-generation space telescopes to high-orbit X-ray stations, These technologies will allow us to search for echoes around distant supermassive black holes, turning the cosmos into a vast laboratory for testing the limits of physics. And for storytellers like you, this shift opens an entirely new frontier. Echoes are no longer just data points. They are philosophical invitations, asking whether we are finally learning to hear the universe speak in its own language. Each signal is a question, each delay a whisper that challenges what we think we know about space, time, and the nature of reality itself. And as we approach the final chapter, remember this: even the physicists studying these echoes admit there is something in the data they can't yet explain. The only question now is whether you are ready to hear it. In the end, all of this leads to a simple truth. We have heard the faint signatures of black hole echoes, but the world has only been shown the surface. Beneath the headlines lies a deeper story, one still unfolding in silence, waiting for those who are willing to listen. And that silence raises a question that goes beyond science. If black holes can release echoes while also swallowing light, if they can speak and mute themselves in the same breath, then what does that say about us? Are we truly listening? Or only hearing the parts that are easy to explain? Picture it for a moment, a lone observer drifting in orbit, staring at the edge of a black hole as a delayed whisper of light curls around the abyss and fades into darkness. No explosion, no dramatic ending. Just a quiet message from a place where time slows and reality bends. Stay curious. Stay critical. Are you ready to listen? And if you want to know what that whisper might actually be telling us, the next chapter is already waiting.